Now, when you solve the energy balance in dynamics, the name of equation will be different, right? If you're using a Hibbeler book, they are using a different names. If you are using the Merriam book, they give you a different name. If you are learning thermofluid or thermodynamic, they will give you a different names. But if you look at the equation, they are actually represent the same thing. They are represent the conservation of energy principle, right? So we have the changes of kinetic energy of the system, and this one implicitly mentioned about time, right? So you have a body at particular instance, and then it have perform some motion. There will be change in the property of the energies, and um, if the value is different, right? That called the change of total energy of the whole body. It means there will be some work. So when you mention about work, you mention about force that act to the body. So the definition of force is that a force equal to a work equal to force time distance travel, right? So, and there are so many type of work available. You have a spring work, you have a force that acting to the body, you have a force that work in the rotational motion, you require some torque, something like that. So all that will be under work W, the symbol work. And then you have to know whether this work is done by the body or the body itself doing the work. Like, for example, uh, if the body is used to turn something else, so you have work out. Now, let's say you have a spring that causes the body to move, so there will be work in. Now you can go to section B, work and energy of the books that I use, and in section 3.6. So the earlier chapter is referring to the motion of particles. So you have to differentiate, right? So the particle part provide you the fundamental that you should know before you go to the rigid body, right? And then on the figures, you can see that force is a vector quantity. You should know the origin of the force, and you can break the force F into component, right? So you have Fn, the substance N mean that the component of force that act normal to the motion of the body, right? And then you have Ft, is a component of force that parallel to the path of the motion, right? Difference between the force vectors and the velocity vectors. The force vectors, the tip of the arrow is pointing to the body, right? Compared to the velocity, where velocity, the tail will be the origin, but the force is different, right? So, and there is a definition of work in this book. They are using U, right? So you don't confuse with the thermodynamics. They are giving you the same thing, right? So you have a force that acting at the distance. Let's say ds. So in order for you to evaluate the work, which in this case is the work is applied from outside, right? Whether it's from string, from your hand, from anything, right? From the outside. So this one should be work in ataupun W in, but in this dynamic book does not tell you about that thing, right? And in order for you to evaluate the amount of work, you need to know the distance, right? So you have the lower limit for the integration, uh, because the force we assume does not depend on. In this case, the force is also depend on the s, right? On the distance travel. So that's why inside the integration. But sometimes you have cases where force is constant. So you can place force outside from the integration, right? And since the force can be break into component, so if you are working in the rectangular coordinate system, so that will be the way that we express the vector f, and the equation actually represent dot vectors, dot product, right? So when you have a dot product, it means that the force you have to take the projection of force, which is parallel to the distance traveled. So the force acting Fx acting on the distance traveled in x, Fy in distance dy, Fz in distance dz. So if we are trying to evaluate using the curvilinear linear coordinate system, where we have only one single coordinate system S, so we don't have to break it into component except to take the component for tangential component for force, and then we set the limit S1 to S2, right? So on the right hand side, we have a chart there. That one we're not using Cartesian, we're not using the spherical polar, but we are using the S coordinate system, right? So we can directly calculate the amount of work based on the area under the graph. Right. Previously, I showed to you that um, the energy balance, right? We have changes of kinetic energy, changes of potential energy. This one will be equal to work added or work being reject from the body, right? Or work done by the surrounding to the body minus work done by the body to its surrounding. Right. So there are example of work W here, or in the book they are using U, right? So sometimes you have the subscript 1 to 2. So it tells you about the time implicitly, or it tells you about the distance, right? So the first example will be called work associated with the constant external force, right? So in this case, when we evaluate the force given by point P based on the figures on the right? So we have a dot vectors. So basically, the vertical component will be removed, and then we have only the component of force that act along the path. So that is the equation that you're going to use. And then we have the second example, which is work that associated with the spring force. So in this case, the definition of spring force is minus spring stiffness, Newton per meter units, and then we have the distance travel, right? So and the force is always acting opposite to the motion of the body, right? So it's different than the first example, right? So as the body is attached to a spring, as it's tried to move away from the initial location, the spring will try to bring it back, right? So if you try to make the body so that is close to a distance, right? The spring will have a force that try to push you away from the body. In this case, we are still call it in energy sense, we call it work added. And there is a evaluation when we replace the definition of spring force inside the energy balance, right? So and then we place it with the limit, right? So we have equation 310. So the differences between this approach, the kinetic approach with the kinematic that we learned before, is that for kinetic, when we consider energy, we need to consider two different time, the position, the orientation, the kinematic description for the body for two different times. So that is the main differences. So if you face a question book or examinations, when you find that the question asking you about two different situations, two different instances, so you need to consider the energy of the body. Right. So we have the third type of work, and this work is situated with the weight, right? So in this case, the force is due to the mass time the gravitational acceleration, and gravitational acceleration will be 9.8 meter per second cos 2, right? Uh, and then we considered on the y direction because we are only covered in our knee. So if you look this work assisted by weight, it's much more clearly that you have to consider two position. You have position. The first position will be the at y1, and then the final position will be y2. So basically, the work associated with the weight u actually is a potential energy change, similar in what we mentioned in the energy balance for thermofluid. Right, I think I'll end my lecture, um, and then we're going to continue that again. And I would like to remind again that on Saturday night, it will be your test one.